Well, this is the 7th presentation on the structure and properties of organic molecules. Hard to believe that we're this far along. We only have 5 more. We have 2 on drawing conformations, and then there'll be 3 on seeing stereochemistry. There is a difference, though, between these 2 boxes that we're ending with and the first 4 that we've covered. In the first box, we had to know, again, how to build structures from carbons, nitrogens, and oxygens. And, of course, there would be many constitutional isomers of this penicillin. But the point was, with these first 4, was learning how to simply see skeletal structures, how to draw them, and then how to see into them what's there. Not what we're proposing, or I guess we in a sense are with theories, but what is represented by these skeletal structures. And we're almost done, because as we go into these next 2 boxes, really the focus will be taking the skeletal structures and considering rotation around bonds, that's conformations, or taking penicillin and seeing relationships that this has to other, I guess, structures like penicillin. In the constitution they're the same, but having, instead of a wedge here, maybe a dash. Now, of course, that wouldn't be penicillin, because penicillin is not only connected in a particular way where things are bonded, but penicillin has orientations, or how things are bonded, set in particular ways. It's what we call regio and stereo specific. Many drugs in the body have to be both regio and stereo specific, because the body has regio and stereo specificity, pockets where orientations matter. So we're almost done with what I would call just the ability to do structural analysis. These last 2 boxes, we're going to be looking at, again, just the conformations within a skeletal structure, so things are going to have to be moving. And then the last one, looking at relationships, other structures that are connected, just like this one is, as far as where things are bonded. But orientations may differ, where we may have a dash here, and this stays wedge, or they're both dash. That would not be penicillin. All right, so let's finish our discussion on acidity and basicity. We said trying to find acidic sites, we're really exposing the compound or thinking about what it would do in the presence of hydroxide. Now, you say, well, that's not a structural thing. Well, yes, it is. We're still trying to find where this has a tendency, a propensity to give up a proton. That doesn't mean we always have to have it act as an acid, but we'd like to know where it would react if it was in the presence of a base. And we found that areo, the acrostic, was very important. Areo, atom, resonance, inductive effect, and orbital. I hope you can see that. That's on the screen, but we'll put it up here. A-R-I-O. Atom was considered in the stabilization of what's left if this takes a proton. So we looked for protons that were on the right atom, those that are most electronegative, and you really come down to these 2, the nitrogen and the oxygen. But the winner is certainly the oxygen. The atom that would be left with a negative charge, if this takes that proton, would be an oxygen, the atom. What's the R stand for? Resonance. If this atom left with a negative charge delocalizes by resonance, we go to an oxygen with the negative charge. So if negative, that negative could delocalize between 2 oxygens, and that's a good thing. Lowering the energy of that anion left behind, if this takes the proton, helps increase the acidity of that proton. That was Monday. We looked at, I guess, other, very briefly, inductive effect and orbital, but these are very important, A and R, in that acrostic. Inductive effect just considers, are there fluorines to help stabilize the negative charge? Orbital considers, is the negative charge in an orbital that has more S character, then it's more stable. But today, we want to consider, well, okay, that's fine. If I were to look at penicillin, I would know that this proton is most acidic. This structure has an acidic proton here. The second most acidic would probably be here. But what if we changed the day? What if we considered penicillin not giving up a proton, but taking a proton. Where would this proton bind? Where would be the most basic site? We still come back to ARIO, but we use it in a different way. Orbital kind of shifts up, say AORI. I mean, it kind of shifts up to this position between A and R. It becomes more important. So we're going into basicity. We're going to still consider atom, orbital, resonance effect, and inductive effect, but we're going to change the order. So which structure below, we're asking a new question, is not most acidic, but we're asking the question, which is most basic? And again, what does that mean? That means we're accepting a proton, not giving up a proton. So it's important to know what the question is, and we're asking of these molecules. We're asking which of these, from this day, in this question, which is most basic. To start this question, consider the partial charges, this is very important, of the initial structures. So in other words, we want to know, as this proton's coming in, accepting a proton, so plus H plus H plus, that's what we're asking, how likely are you to pick up a proton, not give it away, but to take a proton. We want to know where the partial charges are. Why? Because we know something partially negative would love on this positive. So if we look at ethanol, it's pretty clear that we have no pi bonding, inductive effects reign. There's no chance for partial charges set by resonance. We can draw in our lone pairs. And we know inductively this oxygen is more electronegative than the carbon and hydrogen it's bonded to. It would be partially negative. The carbons in like manner that it's bonded to, and the hydrogen that it's bonded to, would be partially positive. So we're just setting partial charges based on the inductive effects we see in this structure. And again, this is sort of building on all that we've done with seeing orbitals, past letters and lines, seeing inductive effect and resonance effects, being able to see behind these skeletal structures. So we're just doing that here. Yes, that oxygen's sp3, and there's no pi bonding. So that would be the place where I'd most likely put the proton. So we're going to consider the conjugate acids that would be formed if this oxygen takes the proton. I still have a lone pair left, but it now has a positive charge. This oxygen has accepted the proton. It's taken its two that it owned, and now it's sharing. I'll circle that one. We'll say it's this one that we just bound. And these are the two electrons that came from the oxygen. It went from sharing to owning. It still has ownership of one lone pair, but it went to sharing with the other. So it's losing. So it's becoming positively charged. And you can also follow, well, if I'm accepting a proton that's positive, I'll probably have to be positive because we don't lose charge. Now we can do the same thing with B, but I want to be careful here. I want to just point out some differences. It has only one lone pair where nitrogen has two, it has one lone pair where oxygen has two. It is partially negative, just like oxygen. And the carbon off of it and the hydrogens off of it would be partially positive. But we do want to note some differences. The oxygen is more electronegative than the nitrogen, meaning more desirous of its electron density. It pulls it in tight around the nucleus. The nitrogen, not so much. It's more electronegative than the carbon. That's why we give it a partial negative charge. But its lone pairs are more active because they're not pulled in as tight towards the nitrogen. It's not as electronegative as oxygen. So we can look on the front side. This is called the front side, just kind of considering before acceptance of the proton. We can look at front side issues and say, hey, really the lone pairs are not equivalent. Yes, there's two on this oxygen, and yes, there's one on this nitrogen, but they're not the same. These lone pairs are a little more active because they're at higher energy state, because they're not drawn in as tight to the nuclei as they are with the oxygen. So they're more reactive. But you can also go to the back side to confirm that this is going to be more basic than the oxygen by looking at the stability of the conjugate acid So we're going to have to put that proton that we are going to circle, put that on. It has a positive charge. We accepted that proton. You already had 2. Now the oxygen with positive charge is less stable because it's more electronegative than the nitrogen with positive charge. So this would be more stable. That's a backside consideration, but they go together. More reactive lone pair to begin with, and once it's bound to the proton, a more stable cation. So that right now B is the stronger base than A. Now I said the acrostic ARIO kind of changes with basicity. If you're asking for basicity of some molecules, think AORI. AORI. Orbital becomes important. We're going to see that with C. This oxygen that's in a pi bond is a polar. We could tag it as such. Polar. This oxygen's in a single bond, but next to a pi bond. It's an oxygen with lone pair next to the pi bond. It's a pusher. So we always say have these two work together, and we could draw a resonance form for that, but this is going to be fairly significant in its partially negative charge. In like manner, this oxygen will be fairly significant in its partial positive charge. You'd think, oh, then this is my winner, because it has a greater partial negative charge than any of these two. Be careful. Orbital becomes really important. This oxygen's lone pairs, 2 of them, are in what orbitals? The lone pairs. We already know these are in sp3 because the oxygen's sp3, and these are in sp3 hybrid orbitals. But what I'm asking is what orbital are these lone pairs in? I hope you're saying sp2. sp2, sp3, if these 2 oxygens were pitted against each other, atom to atom, both partially negative, O versus O, orbital would be the second thing we consider. The more p character, the higher the energy. The higher the energy, the more reactive. Less p character, lower energy, less reactive. So C is less reactive than A in basicity. And we already said A is less reactive than B, because atom, nitrogen, everything else being equal, sp3, it's got a lot of p character in its lone pair. It's partially negative. Nitrogen's more reactive than oxygen. So this is kind of a flip. A lot of students want to just say O's are more reactive in acid-base reactions. Now be careful. You got to know what day you're asking, what day you're on, or what question you're asking. If you're asking about acidity, yeah, go to protons that are on oxygens. If you're asking about basicity, which is going to pick up a proton, go to nitrogens that are sp3. And then go to nitrogens that are sp2, and then go to oxygens that are sp3, and then oxygens that are sp2. So you have to go nitrogen first, sp3, sp2, and then oxygen, sp3, sp2. Again, assuming all those are partially negative. We want to make sure we're on a site that's partially negative. All right, so this conjugate, if we did protonate, we would protonate here. Kind of running out of room here, but let's put the proton on this oxygen. It'd have a positive charge. This would be the conjugate acid. But right now we know our bases. This is number 1 because it's the atom and its orbital is sp3. It's nitrogen and it's sp3. This is 2 because it's oxygen and sp3. Orbital being important. And then sp2 oxygen is right now 3 of these. And we know this one is not going to have much basicity. Folks, if a chloride doesn't like to be protonated, and that's full negative, it's very unlikely that a chlorine in a neutral structure with just a partial negative charge is going to want to be protonated. We can show it, but it's not going to happen to any great degree in solution. You might get a little bit, I guess, and maybe there's some chance for catalytic amounts, but we're talking itty-bitty. This is an unstable conjugate acid. This, again, doesn't want to be protonated when it's negative. Why the heck would it want to be protonated when it's partially negative? So this would be 4. All right, so that's how you approach basicity. And again, I would surmise that nitrogens that are sp3, then nitrogens that are sp2, go after those. Orbital, we're seeing its importance. And then oxygens that are sp3, if you can't find these that are partially negative, again, all these being partially negative, oxygen that's sp3, oxygen that's sp2, we're really looking at A and O and not considering at all resonance. Now, does this come into play? Drawing resonance forms for the cation? Sure. We can kind of see that with C here. This is the only one where the positive charge could be moved from the oxygen to the carbon to the other oxygen. But still, even though with those 3 resonance forms that stabilize the positive charge, 1 and 2 are still more basic. Orbital is that important. Alright, that's it. Now again, inductive effects, I guess in general, the greater the number of halogens, the less basic that neighboring lone pair on the nitrogen or oxygen will be. Or actually, if you halogenate, you're actually causing problems. You're pulling away the electron density, the very electron density you want to bind to a proton. So halogenation would be bad if you want basicity. All right, that's it. We are done with our 7th recording, and we are now heading into our last 5. We're rounding the corner and coming back up to 12 o'clock. These last 2 are really focusing again on not partial charges, resonance, inductive effect, acidity, basicity. They're really looking at just the 3-dimensional look of a molecule and conformations within a molecule. That's it. Bye-bye.